Download this code from codegive.com, link in the description below. Deep dive into vector search versus semantic search, concepts, differences, and code examples. Both vector search and semantic search aim to improve information retrieval beyond traditional keyword-based searching. They leverage the power of machine learning and natural language processing to understand the meaning and context of queries and documents, allowing for more relevant and nuanced results. However, they differ in their core methodologies and practical applications. This tutorial will break down these concepts, highlight the differences, and provide Python code examples to illustrate each approach. Traditional search limitations *. Before diving into vector and semantic search, it's important to understand why traditional keyword-based search falls short. Keyword matching *. It relies on exact or near-exact matches of keywords in the query and the document. Lack of semantic understanding *. It doesn't consider the meaning of the words, their relationships, or the overall context. Car and automobile are different words, and traditional search might treat them as entirely separate terms. Poor handling of synonymy and polysemy *. Synonyms are treated as distinct terms, and a single word with multiple meanings, polysemy, can lead to irrelevant results. Vulnerability to query drift *. A slight change in the wording of a query can significantly alter the search results. 2. Semantic search, unveiling meaning. Semantic search attempts to overcome these limitations by understanding the intent and meaning behind the query and relating it to the meaning of the content being searched. It aims to provide results that are relevant even if the query doesn't contain the exact keywords present in the document. Key concepts in semantic search *. Knowledge graphs * represent information as a network of entities and relationships. Semantic search can leverage knowledge graphs to infer connections between concepts and provide more comprehensive results. For example, a knowledge graph might link Apple, the company, to Steve Jobs and iPhone, allowing a search for CEO of Apple to effectively utilize this information. Named entity recognition, NA identifies and classifies named entities, people, organizations, locations, dates, etc., in both queries and documents. This allows the search engine to understand the specific entities being referenced and refine the search accordingly. Natural language understanding, NLU, a broader field that encompasses various techniques for analyzing and understanding natural language. It involves tasks like part-of-speech tagging, dependency parsing, and sentiment analysis, which contribute to a deeper understanding of the query's intent and the document's content. Query expansion * expands the query with synonyms, related terms, and alternative phrasings to increase the likelihood of finding relevant documents. Contextual understanding * considers the context surrounding the query and the document to disambiguate word meanings and identify relevant information. How semantic search works, simplified. 1. Query analysis * The search query is processed to extract its meaning, identify entities, and understand the user's intent. NLU techniques are applied to parse the query structure. 2. Content indexing * documents are analyzed to extract semantic information. This may involve building a knowledge graph, identifying named entities, and extracting key concepts. 3. Meaning matching * The semantic representation of the query is compared to the semantic representations of the documents in the index. 4. Relevance ranking * documents are ranked based on their semantic similarity to the query. Code example, semantic search using sentence transformers, conceptual. This example demonstrates a very basic form of semantic search using pre-trained sentence transformers. It doesn't incorporate all the complexities of a production-level semantic search system, knowledge graphs, sophisticated NLU, etc., but it illustrates the core principle of comparing semantic representations. Explanation *. One sentence transformer *. We use the sentence transformer library, which provides pre-trained models that can encode sentences into dense vector representations. These embeddings capture the semantic meaning of the sentences. To encode, * the model.encode method converts the documents and the query into their respective vector embeddings. 3 cosine_similarity, * cosine similarity measures the angle between two vectors. A smaller angle, closer to 0, indicates higher similarity. We calculate the cosine similarity between the query embedding and each document embedding. For argsort, * this function returns the indices that would sort the similarities array. We use it to find the indices of the most similar documents. ::-1 reverses the sorted indices to get the results in descending order of similarity. 5 output * the code prints the query and the top 3 most similar documents, along with their similarity scores. Key advantages of semantic search *. Relevance * provides more relevant results by understanding the meaning and context of the query. * handles synonymy and polysemy. * can handle synonyms and polysemy by considering the semantic relationships between words. Improved recall * may find documents that wouldn't be found by keyword-based search because it's less reliant on exact keyword matches. Key disadvantages of semantic search *. Complexity * implementing a robust semantic search system is significantly more complex than keyword-based search. Computational cost * semantic analysis and indexing can be computationally expensive. Dependency on NLP models * performance depends heavily on the quality of the NLP models used for understanding language. Cold start problem * if there is not enough semantic information available, example a new knowledge graph or a lack of labeled data, performance may suffer. 3. Vector search, similarity in vector space. Vector search, also known as similarity search, focuses on representing data, text, images, audio, etc., as high-dimensional vectors and then finding data points that are close to a given query vector in the vector space. It relies heavily on the concept of embeddings, which are numerical representations of data that capture its key features and relationships. Key concepts in vector search *. Embeddings * dense vector representations of data generated by machine learning models. These embeddings aim to capture the semantic meaning of the data. Word embeddings, like word2vec, glove, or fast text, are used for text, while models like ResNet or Clip can be used to create embeddings for images. Sentence transformers, as used earlier, are great for document/sentence embeddings. Vector databases * specialized databases optimized for storing and querying high-dimensional vectors. They typically employ techniques like approximate nearest neighbor, and search to efficiently find the most similar vectors to a query vector. Examples include Pinecone, Fayus, Annoy, Milvus, and Grant. Approximate nearest neighbor, and search * a family of algorithms that find approximate nearest neighbors efficiently. An algorithm sacrifice some accuracy for speed, making it feasible to search large vector databases in real time. Common and techniques include hashing * locality sensitive hashing, LSH, maps similar vectors to the same hash buckets. Quantization * reduces the memory footprint of vectors by representing them using fewer bits. Graph-based indexing * builds a graph where nodes represent vectors and edges connect similar vectors. How vector search works * 1 Embedding generation * data, documents, images, etc., are passed through an embedding model, example a sentence transformer for text, to generate vector embeddings. 2. Vector indexing *. The embeddings are stored in a vector database and indexed using an algorithm for efficient retrieval. 3. Query embedding *. The search query is also passed through the same embedding model to generate a query vector. 4. Similarity search *. The vector database is queried using the query vector. The N algorithm efficiently finds the vectors in the database that are most similar to the query vector. 5. Result retrieval *. The database returns the data points, documents, images, etc., associated with the nearest neighbor vectors. Code example, vector search using FAIS. This example demonstrates a basic vector search implementation using the FAIS, Facebook AI Similarity Search, library. FAIS is a popular library for efficient similarity search in high-dimensional spaces. Explanation *. 1. FAIS.index flat L2 *. This creates a FAIS index using L2 distance, Euclidean distance, to measure similarity. L2 distance is a common choice for vector search. Other options include FAIS.index IVF flat, inverted file indexing, for larger datasets, and FAIS.index HNSW flat, hierarchical navigable small world graph, for improved performance with high accuracy. The best index type depends on the size of your dataset, the dimensionality of your vectors, and the desired balance between speed and accuracy. 2. Index.add *. This adds the document embeddings to the FAIS index. 3. Index.search *. This performs the similarity search. It takes the query vector and the number of nearest neighbors to retrieve, k, as input and returns the distances and indices of the k nearest neighbors. 4. Output *. The code prints the query and the top 3 most similar documents, along with their L2 distances. Lower distance implies greater similarity. Using Pinecone, Managed Vector Database. Pinecone provides a managed vector database service, simplifying the process of storing, indexing, and querying vector embeddings at scale. Here's an example of how to use Pinecone for vector search. Key advantages of vector search *. Scalability *. Vector databases are designed to handle large datasets and high query volumes efficiently. Flexibility * can be used with various types of data, text, images, audio, etc., as long as they can be represented as vectors. Speed *. And algorithms enable fast similarity search even with millions or billions of vectors. Simplicity *. Once the embeddings are generated, the search process is relatively straightforward. Key disadvantages of vector search *. Dependency on embeddings *. The quality of the embeddings is crucial for the performance of the vector search system. Embedding model selection * Choosing the right embedding model for the specific task and data is critical. Lack of explainability * It can be difficult to understand why a particular result was returned because the similarity is based on abstract vector distances. Cold start problem. Embedding training. Creating good embeddings usually requires training a model on a large dataset relevant to the domain. 4. Key differences and when to use each ***. Here's a table summarizing the key differences and use cases for each approach. Feature vector search. Semantic search. Core mechanism. Similarity in vector space. Understanding meaning and intent. Data representation. Vector embeddings. Knowledge graphs, semantic networks. Focus. Finding similar vectors. Finding relevant information based on meaning. Method. Embedding similarity computation, cosine similarity, etc., NLP and knowledge representation. Use cases. Image retrieval, recommendation systems, similar document search, question answering, chatbot development, information extraction. Computational cost relatively low, after embedding, high, due to NLP processing. Explainability low, potentially higher, with knowledge graphs. Scalability excellent, can be challenging. Data types works with most data types, more focused on text and structured data. When to choose vector search asterisk. Asterisk large-scale data sets asterisk when you need to search through millions or billions of data points. Asterisk multimedia content asterisk when you are dealing with images, audio, or video data. Asterisk recommendation systems asterisk when you need to find items that are similar to a user's past preferences. Asterisk speed is critical asterisk when you need to retrieve results in real time. Asterisk black box acceptable asterisk when you primarily care about finding relevant items and less about understanding the underlying reasoning. When to choose semantic search asterisk. Asterisk complex queries asterisk when you need to understand the intent and context of the query. Asterisk question answering asterisk when you need to provide direct answers to user questions. Asterisk chatbot development asterisk when you need to understand user utterances and generate appropriate responses. Asterisk knowledge intensive applications asterisk when you have a knowledge graph or other structured data that you can leverage. Asterisk explainability is important asterisk when you need to provide users with insights into why a particular result was returned. Asterisk need to disambiguate multiple meanings asterisk where context helps resolve ambiguities. Hybrid approaches. In some cases, a hybrid approach that combines the strengths of both vector search and semantic search can be beneficial. For example, asterisk semantic enrichment plus vector search asterisk use semantic analysis to enrich the data with metadata, example named entities, topics, and then use vector search to find items that are similar based on both semantic similarity and metadata matches. Asterisk vector search plus semantic re-ranking asterisk use vector search to retrieve an initial set of candidate results and then use semantic ranking to re-rank the results based on their semantic relevance to the query. Asterisk knowledge graph guided vector search, use entities and relationships in a knowledge graph to refine the query and guide the vector search towards more relevant results. 6. Conclusion. Vector search and semantic search are powerful techniques that can significantly improve information retrieval. Vector search provides scalability and speed for finding similar items based on vector embeddings, while semantic search focuses on understanding the meaning and intent of queries. The choice between these approaches depends on the specific requirements of the application, including the size of the dataset, the complexity of the queries, and the importance of explainability. Hybrid approaches can often provide the best of both worlds, combining the strengths of vector search and semantic search to achieve optimal results. Choosing the right technique, or a hybrid, is critical for building efficient and relevant search systems.